This is interesting features of the X86-64 architecture as recorded during the OpenVMS Bootcamp 2016 in Nashua.
We've had this one, so I'll not do that one again. I've got a short introduction. Then I'm going to go into a few of the areas that we need to look at. So I'm going to look at segmentation. I'm going to look at processor modes. I'm going to look at the early boot. And I'm going to look into one of the new architectural features called Intel TSX. So when you're writing or porting an operating system, you need some documentation. You need something that specifies the architecture to the level that you need to know this architecture to be able to write something like an operating system for it. So for the VAX, the very minimum you need is the VAX 11 architecture reference manual. And I know it doesn't give you everything you need to know to implement an operating system for a particular model of VAX, but most of it's in there. For the alpha, similarly, there's the AXP architecture reference manual, which is sort of like a vetted for the public version of the internal systems reference manual. For Itanium, you get the Intel Itanium Architecture Software Developers Manual, and likewise for X86-64, you get the very long name Intel 64 and IA32 Architecture Software Developers Manual. And just for fun, I'm going to show you what these books look like. This is a bookshelf that I'm hoping to fill. So I'm going to add VAX in. 1 inch of documentation. We're not going to fill our bookshelf this way. So let's add alpha. That's 2 inches of documentation. Tells you pretty much everything you need to know about the alpha architecture. Nah, still not very impressive. Let's add Itanium. Oh, 5 inches. Let's see what happens when we add X86. 12 inches of documentation. So, unfortunately, we didn't entirely fill the bookshelf, but we got well on our way, I think. So this is just to give you a bit of an idea of the amount of specification details that you need to wrestle through to understand this architecture. And there's a whole lot of options available to you, and there may be 3 or 4 different ways to approach a certain problem on this architecture, where on alpha there would really only be one way that really stood out as this is the way to do it. So what's important for us is that we really understand all of the nooks and crannies of this architecture, because if we don't, we may choose a certain implementation path, whereas if we had known of some other feature of this architecture, we would have done something different that would save us a lot of time or run a lot faster. Yes?
The multiple books, is there a logic to the fact, or is it just to divide up the 12 inches?
Well, there's some logic to it. There are, let me see, well, no, the picture's not clear enough to see it. I think there's 2 books that are like an introduction to the architecture, and that basically tell you everything you need to know about the architecture if you're not an operating system developer. Then there's, no, I think that's just the 1 book. Then there's 3 books that are everything in addition to that you need to know when you are building an operating system. Then there's 3 books that are basically a list of all the instructions and what they do, and they have little bits of pseudocode that write out what each instructions do, and sometimes you read the description of an instruction, and yes, it tells you what the instruction does, but it may not be entirely clear what that instruction does if an interrupt comes in the middle of it. And you need to read like the pseudo code that explains in much more detail what the instruction does and how it goes about it to figure out some of those details. So you really want to read that, especially when you're developing an operating system and you're depending on everything to happen just right. And then the other two, I slightly cheated. You don't actually need those if you're writing an operating system, but they're useful. One of them is about all of the instruction set extensions and how you can find out whether they're supported and what the caveats of some of those may be, and we want to use some of those extensions possibly, so having that is a good thing. And the other one is the compiler writer's optimization manual. And that will tell you if you're compiling code for x86, it's a bad idea to use this sequence of instructions. It's better to reorder them that way because the processor can handle it better. And those rules are different for each microarchitecture, and it gets very complicated. But it's when you're writing assembly level code as part of an operating system, having those sets of guidelines and sort of basic rules, it also tells you you probably want to put this structure on a 4-byte boundary, things like that. That's the sort of thing that's good to know when you're writing an operating system. So, yes, you almost need all of that.
And would this bookshelf just be the Intel books, and maybe have a set of AMD books?
AMD has a somewhat similar set of books. For 99% they'll have very similar content, just written by different people in a different style. The 1% that's very different is, well, very different. When you get into things like the virtualization extensions, AMD and Intel have basically taken the same approach, but both came up with their own implementation. There are some things that you need to be aware of where some instructions Intel chose not to put into their 64-bit mode and AMD did. Fortunately, where that's the case, there's usually something available that works on both of them. You just need to be aware of those limitations. So yes, if you want to run on both Intel and on AMD, and you're writing an operating system, you'll want a similar set of books from AMD as well. So that would fill the bookshelf. So I'm just going to over a few of the details of this architecture. I can't go into everything, but I'm hoping to give you a bit of a sample of the kind of architectural features that we are looking at and trying to figure out how does this figure into our plan. So this is not an in-depth exercise. It's certainly not a broad exercise, but it will just give you a few tidbits that will hopefully give you a sort of feel of the investigative process that we're going through. So there's something called segmentation. And it started out in the 8086 and 8088 processors as a way to extend the address space from 16, you have 16-bit registers, and typically that means you can only address 64 kilobytes of memory. So segmentation was invented as a way to address a 20-bit address space using 16-bit registers. So they added some 16-bit registers called segment registers. And you put a value in there, and it selects which 64-bit portion of the address space you're interested in. So, for example, if you have an instruction that moves the contents of register AX into, or the contents of the memory pointed at by register AX to register BX, you're going to take the value of the DS register, the data segment, shift it left by 4 bits, and then add the value of the AX register at it to get to the effective address. So this is a relatively simple scheme, although managing the values of the different segment registers gets a bit tedious, and it means it's difficult to address more than 64 kilobytes of memory in any one operation. So there's separate segment registers for the code segment. So your code can live in a different 64-bit space of the 20-bit address space than your data. There's a separate one for data. There's a separate one for stack. Sorry. And then there's an ES segment register, dubbed the extra segment register. And you can put a prefix in front of your instruction to say, normally this instruction would reference memory in the DS segment, but I've loaded some special value in the ES segment because I want to do something with memory that I'm normally not touching, and I now want this instruction to reference the ES segment. So you put an ES colon prefix in front of it. In some of the string manipulation instructions, you basically take a source and a destination operand, and there the source index is relative to the data segment, and the destination index is relative to the extra segment. So if you're moving data around, they came up with a way to make this a bit easier to move data from one 64-bit segment to another 64-bit segment. But it means that you need to be aware of this. If you just go coding it and think everything references the DS segment, now all of a sudden you get a surprise. So this is a simple, effective way to address the entire 1 megabyte memory space using 16-bit registers. So when we get to 386 protected mode, CS, DS, SS, and ES are no longer segment registers. They're now segment selectors. We now have a 32-bit address space, and we have 32-bit registers. So in theory, you could address the entire address space using a single register. And in fact, that's what most programmers do. That's what most operating systems do. They don't use this segmentation. They treat the entire address space as a one flat address space. But if you want, you can use the segment selector, and it no longer contains an actual address. It contains an index into a table that contains segment descriptors. And a segment descriptor defines the base address of a segment. It defines its limit or its length. And it defines the protection bits for the segment. So you can have a code segment that's only accessible in kernel mode, or you can have a data segment that's accessible in all modes. And this works in addition to, on top of paging. So if you use paging, you can use segments on top of it. You can also use segments without using paging. In fact, you always have to use segments, but a lot of operating systems simply have segments that span the entire virtual address space. So effectively not using segments. The way it works is something like this. You have your GDTR, the register that points to the global descriptor table, the GDT. The GDT, or the global descriptor table, is a list of selectors, and your DS segment is now simply an index into that list. So it points at one of these selectors. The selector has a base address that points at a place in virtual memory, and it has a limit that says at so much, and that's where this segment ends. And then, of course, on top of that, you can have paging. So if you access something through the DS segment, and the DS points to this selector, address 0 now lives here, rather than 0 all the way at the beginning of virtual memory. So this can get a bit confusing. So it's basically another protection layer on top of paging. So it was popular when in the early days, but it pretty rapidly lost its meaning, and everyone now does paging, and segmentation doesn't really play a big role anymore. Which is why when you get to the 64-bit mode, the base and the limit in the segment descriptors are now being ignored. The mechanism is still there, even in 64-bit long mode, but for the CS, DS, ES, and SS segment selectors, only the protection bits matter, and some of the other bits that describe what kind of segment it is. But the base and the limit are being ignored. Virtual memory simply starts at 0. That's it. So it means that for these segment selectors, there basically is no segmentation anymore. But for the FS and GS registers, which I forgot to mention, they added 2 more segment selectors that programmers basically can use as they see fit, FS and GS. They added that when they added 386 protected mode. So in long mode, the FS and GS segment selectors are now special, because for them, the base and the limit do matter. And so why would you do that? And the answer is, once you get it, it's somewhat simple, but to get to that understanding may be more difficult. You want to find stuff. And if I'm writing an operating system, what I'm interested in is some specific information that is not tied to the process that's currently executing, but that's tied to the processor that I'm currently running on. And so in OpenVMS, what we're going to probably be doing is using the GS segment selector to point to a different area of virtual memory on each processor. And the piece of virtual memory it will point to is something like an index into a table that will allow us to find the per CPU slot and other CPU database related stuff. This is how Microsoft Windows uses the GS segment selector. This is how Linux uses it. So it's probably a good idea to do it. The reason it's a good idea to do it is because on X86 there's no easy way to ask the processor, what processor number are you? And the processor will respond, I'm CPU 0, when you can use that as an index into a table to look up some CPU-specific data. Jamie?
How does this change when you start looking at virtual environments? Because then that's then some hypervisor which does have the management layer, doesn't it?
Yes. Getting into that is a recipe for a headache. You basically, hypervisors, well, traditional hypervisors tended to have to fake a lot of these things. They had to intercept a lot of things that were happening in the virtual machine and basically swap things underneath it and things like that. Now, with the virtualization extensions that AMD and Intel have been adding to their CPUs, a lot of that burden is taken away from the hypervisors and is implemented in the CPU itself. So the CPU will do a lot of shadowing of registers and things like that, but it will only do it for a single layer of virtualization. So running a virtual machine within a virtual machine, the second virtual machine can't use any of these features if the machine at the bottom is using them. But yeah, there's no easy way to get like a processor number out of an Intel X86 register. There's no CPU who am I instruction that gives you a nice number that you can go to look in a table. So you need to figure out, well, how else can I do this? And it turns out that the GS segment is a good way to do this, and it's the only way to do it if you want to do it really fast. Likewise, the FS segment selector could be used for finding things like thread local storage, something that stays with a thread rather than be generic for the entire process. Yes, there is, although somewhere that's disabled in the firmware. No, it's a good question. One of the things, of course, that we need to think about is, well, if there's no easy way to get a nice consecutive number, how are we going to get it? What you have to do on an Intel processor to get something resembling a CPU number is go talk to the local interrupt controller. The local interrupt controller is, now it's more or less part of the processor. It used to be a separate chip, but it talks to all the other local interrupt controllers in the system, and among them they sort of build a topology of the system, and they will give you a number. However, getting that number takes more clock cycles than going through something like the GS register, and the number it gives you is not consecutive. In a lot of cases it is, but in a lot of cases it's not. And I'll tell you when it's not. If you have a system with more than one chip, and the number of cores on these chips is not a factor of 2, you will not get consecutive core numbers out of ACPI. There will be gaps there because ACPI is based on, I have one bit at the very bottom that represents the co-thread, and then I have a few bits that represent the core within the chip, and then I have a few bits that represent which chip it is. So if the number of cores on the chip is not a power of 2, there'll be a gap there. And so that makes it really impractical to use that number as an index. So rather what we do is during early boot, we identify what all these different numbers in the system are. We give them each a nice consecutive ID, and we may do some reordering because in VMS, one of the things that we can only right now support 64 cores. And you can very easily go and buy an Intel system that has 60 physical cores. And if you enable hyperthreading on that box, you have 120 co-threads. Now, we cannot use all of those. We can use up to 64 of them. So in that case, it's probably a good idea to use one of the co-threads of each CPU, using all of the CPUs, but only using a single co-thread on most of them is, I think, preferable to only using half of the CPUs and using the 2 threads on them. So if we do some reordering in the processor numbers, we can ensure that the lowest 64 processor numbers are all on different chips. So that's why we come up with our own number for it, and we can use that as an index to go into a table, and then we'll use the GS segment selector basically as a place to quickly find this number and to quickly find some of these pointers to some of these tables. So I hope that's somewhat clear. So that brings me to processor modes. And scary. This is a diagram of the processor modes available in a current 64-bit Intel chip. There's something called system management mode that was introduced in one of the 386 iterations. That runs under the control of firmware. As an operating system, you don't really have any way to get into it. So here you still have the real mode, which is 16-bit registers, 20-bit address space. Then you've got protected mode, originally 16-bit, then also 32-bit. Then if you're running in protected mode, you may want to run some processes that need to think that they're still running on an 8086. So there's something called virtual 8086 mode. all of this together is now in our 64-bit world called legacy mode. And from legacy mode, when you can go to something called long mode. But even in long mode, you still have something called compatibility mode, which again uses 32-bit segments and things like that. And then finally, there's 64-bit long mode. And the arrows show the different transitions you can go through to get from one mode to another. And this is what I think makes the life of a Microsoft kernel developer an absolute nightmare. Because at Microsoft, when you're developing Windows, you have to deal with legacy code that can't run in 64-bit long mode, so they need to use this compatibility mode. And it was not too long ago that they needed to use this virtual x86 mode and things like that. And if you need to use all these details, it gets very, very ugly very, very quickly. So fortunately, as VMS, we don't have legacy code on x86 to deal with. So we can focus on running in 64-bit mode and basically more or less forget about that. We don't need it. Or do we? I'm going to give it to you. Early boot. So during early boot, UEFI controls the machine. On x86, we're only going to be running on systems that have 64-bit UEFI firmware. When our OS loader starts, when you start that from the UEFI firmware, it runs on a single CPU, the primary CPU. And in UEFI firmware speak, the primary CPU is called the BSP, or the bootstrap processor. And UEFI has gone through all of the steps to put that processor into 64-bit long mode. So it's enabled paging, it's enabled protection, it's enabled 64-bit. We're good to go. This processor can start running a 64-bit operating system right away. But the secondary CPUs, or as UEFI likes to call them, the APs, the application processors, get initialized by the UEFI firmware, and the UEFI firmware needs to do this because it needs to be able to tell the operating system, these are the processors in your systems, so it needs to identify what they are, and to be able to identify them, it needs to start them. So it starts them, initializes them, and then basically they execute a halt instruction which kills it. It's no longer running. By the time we get control of the system, the application processors have been stopped, halted, dead, kind of. And the only way to wake up a processor that's in a halted state is to send it something called an Init IP, where IP stands for Inter-Processor Interrupt. So the bootstrap processor queries the ACPI tables to figure out what the other processors in the system are, and it goes through them one at a time, and it sends them one of these Init IPIs. And that's basically a wake-up signal, boot again. And then after the Init IPI, you send it a startup IPI, which has an address associated with it, where it will start executing code. And the AP, it's like it's never been turned on before. It starts executing code, not in 64-bit long mode. It starts executing code in 16-bit, 20-bit address space, real mode. So that means that we have to take that application processor and move it from where it boots here through there to where we need to be. So once we've done this, we no longer ever have to worry about any of the other modes, but this bit of code took me a fair bit of work to write. And there's some code examples that you can find out there that show you how to do it. But of course, we being VMS, we want to do it in a specific way, and we want to understand what's going on. So it was not just a matter of picking up one of these example bits of code and putting it in there. But of course, the starting point for this whole figuring out how to do is, the logical thing to do is to go see how Linux does it. And Linux goes through a number of steps to get there, and by doing a few things at a time, we were able to do them in a fewer steps, which was a fun exercise. But we're now at the point where we can initialize the secondary CPUs and get them where we want them to be in 64-bit long mode. Yes?
When does hyperthreading on or off enter into this chain?
That's a firmware setting. So before we get control of the system, the question hyperthreading on or hyperthreading off has already been decided. And if hyperthreading is off, it's very simple. The ACPI tables will only show us one core or one thread per core. If hyperthreading is being turned on in the firmware, we'll get an ACPI table that tells us there's twice as many processors as there really are. And then it's up to us to figure out that those are actually co-threads. And there's a mechanism to find out what the topology is.
Okay, so with this architecture, there's no way of turning hyperthreading on or off once your system is up.
Correct. Correct. The only thing you can do is not schedule anything onto one of these cores or hold one of the cores. But it's more efficient to have hyperthreading turned off at the firmware level in the first place. So that brings me to something called Intel TSX. And this is something that we're not going to be using immediately. It's just one of the things that's probably in our future, and it's a fun little thing they've added to the architecture that I think is eventually going to make a big performance difference in some of the work that we do. So TSX means transactional synchronization extensions. And basically it's trying to solve the problem of I'm trying to synchronize access to a single piece of data from multiple threads or access to multiple pieces of data. And the way you traditionally do that is by putting some locking around it, like a spin lock. So if there's any chance that a bit of data is going to be touched by more than one thread at a time, you're going to write some locking code. Even if the chance of an actual locking conflict occurring is only very low, you always have to take out the lock and you always have to release the lock after you're done with it. So the idea of Intel TSX is to sort of find a way around that. And the way they do it is you start a transaction, and from that point on, all memory writes that you do are restricted to the local CPU core's cache. It doesn't go anywhere else until you're finished with your transaction, and then all of the changes that you made to memory during the transaction become visible to all other processors immediately. So basically everything you change within that transaction happens atomically if you look at it from the other processors. So the processor you're running on knows what you've changed, and if you try to read a value that you've just written, you're going to read the value you wrote. But if another processor reads that value, it's going to read the original value. And there's two interfaces that will let you use this capability. One of them is a really simple one. It's called HLE, Hardware Lock Elision. And what that basically does is you write your code the way you always have, including taking the lock and releasing the lock, but you put an X acquire prefix in front of the instruction that acquires the lock, and you put an X release prefix in front of the instruction that releases it. And what will happen is the processor will now try to execute this code without actually taking the lock. So it will execute all the instructions, but it will keep everything in its cache. However, if another processor touches any of that memory that we've been touching, now the processor basically rolls back the transaction and does the same thing over again, but now actually taking the lock and doing this non-atomically. So if there's no conflict, the code just goes through without actually taking the lock. If there is a conflict, we roll back and both threads will do this with the lock. So it's a simple way to make it work. And the nice thing about it is these prefixes get basically ignored if you're doing this on a processor that doesn't know about this extension yet. The other model is a bit more complicated. It's not backwards compatible, but it's a bit more powerful. And this is where you, rather than use some instruction prefixes, you use a few new instructions. So the new instructions are xbegin to start a transaction, xend to signal the end of the transaction, and xabort in case you, rather than the processor, decide in the middle of an operation you want to roll it back. So it's more flexible than hardware lock elision, but it's more work on the programmer's part. So if there are any conflicts during one of these xbegin, xend type transactions, what it will do is when you issue the xbegin instruction, there's an address as an operand. That address is sort of like a fallback routine. So if there's a conflict, the transaction is rolled back. None of the other CPUs will ever see that you try to do anything with the memory, and instead it jumps to the address you specified when you execute the xbegin instruction. And you can then decide what you want to do. You may want to try this 3 times and then fall back to doing something, actually taking out a lock. Or you may want to immediately take out a lock and do it the old-fashioned way. So, to example of what the code for that would look like, I've written a very simple spin lock here, and I hope it's readable. Basically, what we're doing here is we're just locking. We're locking a value by exchanging it with a 1. We've just put a 1 into register ECX by clearing it and then adding 1 to it. So we've got 1 in here, and we exchange that with an address in memory. And basically, we put a 1 in memory, and we get back what the value was before we put it there. If the value was 0, great, we've acquired the lock. If the value was already 1, someone else had the lock, and we retry. So we spin in this loop until we find out we have written a 1 where there was originally a 0. Simple spin lock. And then we increment some value somewhere, and then we release the lock again. This is really very simple code. Usually you would do a lot more than simply incrementing a value in between here, of course. So with hardware lock elision, you simply add x acquire to this instruction, and you add x release to that instruction. And what it will do, it will still do the same thing. It will try to acquire the lock, and except that it doesn't. It's watching the cache coherency bus to figure out if anyone else is doing anything with whatever values we're referencing here. So internally, it's taking out the lock. It then, unless the lock was taken, in which case it retries this, which is fine. That just means that somewhere previous there was a conflict and someone else now actually has taken the lock. So that also means that if the other code sorry, no, let's not go there. Sorry. So can acquire the lock, it will simply go through there, but it won't actually write the new lock value to memory. It will only write it to its local cache, which is much quicker. It will then increment the value, same thing, and it will release it. It will move a 0 into its cache line. It will recognize, hey, that's the original value. Basically, we've done nothing with that lock, and it will only increment that value in memory atomically and whatever else you did between here, and the whole locking gets kind of ignored. Unless there's a conflict, in which case we redo this and we do actually take out the lock. So very safe, and this runs on older architectures as well, except of course you don't get the benefits of this.
Could you keep a mechanism where you decide whether you have to take the lock or not?
Right. So what we do is we do an exchange. A compare and, is it a compare? Yeah, a compare and exchange. So we write a value of 1 to memory, and at the same time we want to know, was the original value 1? And this is assuming that that memory location will contain a 0 if the lock is clear, and a 1 if it's locked. So we get back from that instruction what the original value was. If the original value before we did this was already 1, then we're good. Well, we're not good. It means because someone else has the lock. But we have basically written a 1 where there already was a 1, so we don't have to unlock anything. We just repeat it until we've locked it, and we know that we've locked it because it says the previous value was 0.
That's the TSX mechanism, isn't it?
Well, that's the non-TSX mechanism.
So that's still what I'm saying. How do you not take out the lock physically?
Right. By keeping it only in the local CPU's cache line is the underlying mechanism. So the CPU sees whatever it's doing, but none of the other CPUs see it. But the CPU is keeping track of, I've touched this memory location, and I've touched this memory location. And if somewhere between here and there, another CPU touches memory that is on this CPU's, I've modified this list, that's where it decides, I need to forget everything I've done so far, go back to this point, and now actually take out the lock and do everything the old-fashioned way. So that's how it works. With TM, the more sophisticated way of using this, the regular code path becomes very simple. There's an xbegin instruction, then there's your increment this value, and then there's a transaction end instruction, after which you can return from your function. So no locking at all. The thing it's watching for is this value thing. As soon as another processor touches or looks at that value in memory, we roll back whatever we were doing here, and the processor sends us to this address, retry with spin lock. And then this is the old original code where we do it the old-fashioned way. So this is one of the things that we may be able to use in things like queue operations, because there's a lot of locking going on in VMS around queue operations, and in some cases you really need that. In other cases you don't. Where you don't, this is going to be a very nice way to get around some of those issues, because this allows for much more fine-grained locking. What you often see is that you've got a whole lot of different things protected by a single lock. And you take out that lock and you block a lot of different things that may not be related to the little bit that you're doing. So if you're if you want to take out the lock to do this, to touch these bits of memory, and another process or thread wants to take out the same lock to do something unrelated somewhere else completely in memory, you've previously had a conflict and one of the threads had to wait for the other now. And that's on top of the overhead of doing the actual locking. With this RTM mechanism, as long as the actual values in memory that you're changing as part of your transaction are separate from what the other thread is touching, there's no locking involved at all anymore. So this could get some very nice performance benefits in things like transaction processing and things like that, as well as in RQ instructions. So I think this is a useful addition to the instruction set, and I think we'll start making some use of this sometime after we get our initial version of X86 out the door. Any questions on any of this or anything else X86 related? Yes?
So the X-Require is really a prefix? Just like the
Here.
lock is a prefix?
Yes, yeah. So you now, at the expense of adding an extra byte to your instruction, you get this behavior.
Should we assume from the picture you just draw to us there would be any, I guess, impact on how you do, for example, file locking or record locking or I/O locking?
I/O locking, yes. Maybe to a certain extent in some of the underlying primitives. But something like our lock manager has to operate not just on a single box, but across a cluster. And this only works on a single physical box, and it only works on stuff that is in memory. This has no bearing at all on locking stuff that's in the disk, apart from locking bits that are somewhere in a cache. All right, for your attention, and have a nice lunch.